Thank you, Mr. Chairman. The title of my talk today is Selective and Tunable All-Optical Wavelength Converters using Coarse Phase Matched Periodically Poured Lithium Niobate Devices operated by Dual Pumping Scheme. The author is myself from Tokyo University of Science. This is outline of this talk. First of all, I am going to talk about background and purpose of this presentation. The cascaded kite effect in periodically poured lithium niobate devices, PPLN devices for short, has recently been applied to optical communication systems. These are advantages of the PPLN devices. The Quash phase matching wavelength, QPM wavelength for short, can be arbitrarily controlled by the period of the Chi2 grating. The PPN devices also feature ultra-fast response, high efficiency, low noise, compactness, integration compatibility, and high stability. These are applications of the PPLN cascaded Chi2 devices. All optical wavelength converters, phase conjugators, multiplexing switches, and demultiplexing switches using the PPN devices have been reported. Especially, all optical wavelength converters are important for constructing future broadband 40 gigabit per sec WDM networks and their applications. This view graph shows the operation principle of the continuous wave pumped PPLN cascaded Chi2 devices. To convert the signal wavelength, the wavelength of the pump light is set to the QPM wavelength. Then its second harmonic is generated, and difference frequency mixing occurs between the second harmonic and the input data signal, and the idler wave is newly generated. Through this process, which is regarded as 4A mixing in the Chi3 media, the data signal is wavelength converted, and the wavelength converted signal is a phase conjugation replica of the input data signal. This scheme is independent of the modulation format and the signal bandwidth. However, the wavelength of the wavelength converted signal is determined compliantly once the wavelength of the input data signal is given. On the other hand, selective and tunable all optical wavelength conversion, which means all optical wavelength conversion from an arbitrary wavelength to another arbitrary one, has recently been realized by using the cascade of some frequency mixing and difference frequency mixing in the PPN devices. This view graph shows the operation principle of such selective and tunable wavelength conversion using the PPN devices. Let us signal pump 1 and pump 2, which have frequencies Fs, Fp1, and Fp2 respectively, be launched on the PPN device with the QPM frequency of FQPM. To convert the signal frequency, the frequency of pump 1 is set to this value. Then some frequency mixing between the signal and pump 1 generates a some frequency component at this frequency. A wavelength converted signal is obtained at this frequency by difference frequency mixing between the sum frequency component and pump 2. Thus, adjusting these two pump frequencies, we can realize selective and tunable wavelength conversion from an arbitrary wavelength to another arbitrary one. However, a variable signal bandwidth might be strictly limited by the QPM bandwidth. So the purpose of this talk is to review characteristics of such selective and tunable wavelength conversion scheme using the PPN devices. This is outline of this talk, and next I am going to explain the experimental setup for selective and tunable wavelength conversion using the PPN waveguide devices. We first investigate the performance limitation and then demonstrate a 40 gigabit per sec operation. This view graph shows the experimental setup. Two continuous wave pumps were generated by tunable laser diodes, respectively. These pumps were combined and amplified by an erbium-doped fiber amplifier. On the other hand, a mode-locked fiber laser driven at a 10 GHz repetition rate generated signal pulses with a 1 picosec sec-h intensity waveform. The signal pulses were filtered by an optical band pass filter, which controlled the signal pulse width by changing the filter band width appropriately, and then amplified by an erbium-doped fiber amplifier. The signal pulses and two pumps were combined and launched on a 1 cm long, 3 cm long, or 5 cm long PPN waveguide device. Average power of the signal pulses and the powers of pump 1 and pump 2 at the input port of the device were 11.2 dBm, 18.7 dBm, and 19.9 dBm, respectively. These polarization controllers controlled polarization states of the input lights so that they matched with the TM mode of the PPN waveguide device in order to use the maximum nonlinear coefficient D33 of the lithium niobate crystal. These are the device parameters of the 1 cm long PPN waveguide. The cross-section of the waveguide was 12 micrometer square. The QPM wavelength was about 1554 nanometer. The QPM bandwidth of the 1 cm long device was about 320 GHz, and the insertion loss was 4.2 dBA. These are the device parameters of the 3 cm long PPN waveguide. The QPM wavelength was about 100 GHz. And these are the device parameters of the 5 cm long PPN waveguide. The QPM bandwidth was about 60 GHz. Wavelength conversion characteristics of these PPN waveguide devices were monitored by an optical spectrum analyzer and an intensity autocorrelator. Next, we go on to the experimental results and their discussions. This figure shows an optical spectrum of the output from the 5 cm long PPN waveguide device, measured when the wavelength of the input signal pump 1 and pump 2 are 1560 nanometer, 1547 nanometer, and 1572 nanometer, respectively. In this case, the signal wavelength is converted to 1535 nanometer. And the wavelength conversion efficiency at the output port of the device is as high as -6 dB. This figure shows the pulse width of the wavelength converted signal, measured as a function of the pulse width of the input signal in the 5 cm long device. In an ideal case, these pulse widths should be equal for all values as shown in the dotted line. However, when the pulse width of the input signal is smaller than 8 picosec, pulse broadening of the wavelength converted signal can no longer be ignored. This critical pulse width of 8 picosec well agrees with the temporal width estimated from the QPN bandwidth of 60 GHz in the 5 cm long device. On the other hand, this figure shows an optical spectrum of the output from the 3 cm long PPN waveguide device. In this case, the wavelength conversion efficiency is -14 dB, which is 8 dB lower than that of the 5 cm long device. This figure shows the corresponding pulse width conversion characteristics of the 3 cm long device. In this case, when the input pulse width is smaller than 5 picosec, the pulse broadening can no longer be ignored. This critical width of 5 picosec is also in good agreement with the temporal width estimated from the QPN bandwidth of 100 GHz in the 3 cm long device. Finally, I would like to discuss the relation between the critical pulse width to be wavelength converted and the crystal length. As we can see from this figure, the convertible minimum pulse width is proportional to the crystal length. Its ratio is calculated to be about 1.6 picosec per centimeter and can be utilized as a performance metric. For example, 8 picosec pulses can be arbitrarily wavelength converted without serious distortion by using the 5 cm long device. This means that the 5 cm long device is attractive for channel-by-channel wavelength conversion in 40 gigabit per sec DWDM networks. On the other hand, 2 picosec short pulses can be arbitrarily wavelength converted without pulse broadening by using the 1 centimeter long device. This implies that the 1 centimeter long device is attractive for tunable wavelength conversion of 160 gigabit per sec OTDM signals. This is outline of this talk, and next I am going to explain the experimental setup for a 40 gigabit per sec system demonstration using an optimal PPN waveguide device. This view graph shows the experimental setup. A signal and 2 pumps were generated by tunable laser diodes, respectively. A lithium niobate intensity modulator modulated the signal intensity with a pseudo-random bit sequence from a 40 gigabit per sec pulse pattern generator. The 40 gigabit per sec non-return to zero signal and these two pumps were amplified by erbium-doped fiber amplifiers and then filtered out by optical bandpass filters. After combined, they were launched on the 5 cm long optimal PPN waveguide device. Average power of the 40 gigabit per sec signal and the powers of pump 1 and pump 2 at the input port of the device were 9 dBm, 17.8 dBm, and 17.6 dBm, respectively. Wavelength conversion characteristics of the 5 cm long PPN waveguide device were monitored by an optical power meter, an optical spectrum analyzer, and a sampling oscilloscope. Next, we go on to the experimental results and their discussions. This figure shows an optical spectrum of the output from the 5 cm long PPN waveguide device, measured when the wavelength of the input signal pump 1 and pump 2 are 1559 nanometer, 1548 nanometer, and 1567 nanometer, respectively. In this case, the signal wavelength is converted to 1540 nanometer. And the wavelength conversion efficiency at the output port of the device is as high as minus 10 dB. These figures show the corresponding eye patterns of the input data signal and the wavelength converted data signal, respectively. We find that the 40 gigabit per sec non-return to zero signal is successfully wavelength converted. However, the eye pattern of the wavelength converted data signal is contaminated compared with that of the input data signal. This output deterioration is mainly attributed to the interchannel crosstalk induced by unwanted higher order frequency mixing. These figures show the eye patterns of the wavelength converted data signals for various wavelength assignments with the different intervals. In this case, each wavelength interval becomes wider. Therefore, unwanted higher order frequency mixing is reduced, and the output deterioration decreases accordingly. On the other hand, in this wavelength assignment with a narrower interval, the output deterioration increases because of larger, higher order frequency mixing. This is outline of this talk, and finally I summarize this presentation. In conclusion, we have reviewed the characteristics of selective and tunable wavelength conversion from an arbitrary wavelength to another arbitrary one using the cascade of some frequency mixing and difference frequency mixing in the PPNN waveguide devices. Through wavelength conversion experiments using short optical pulses, we have shown that the ratio of the critical pulse width to be wavelength converted and the crystal length is 1.6 picosec per centimeter. The results have suggested a possibility of selective and tunable wavelength conversion of 40 gigabit per sec DWDM signals using the 5 centimeter long PPN device. Thank you very much for your kind attention.